Bromine will react with benzene when iron is introduced as a catalyst. A substitution reaction occurs where a hydrogen on benzene is being replaced with bromine. The reaction will not take place without a catalyst, and so we would need to make sure to include iron in the list of reagents. The observed reaction is called an electrophilic aromatic substitution reaction, and that's named after bromine, which is an electrophile. So we name the reactions after what's being added as a reagent. And so since we're adding an electrophile in bromine, we call it an electrophilic aromatic substitution. So as a review, in Chapter 8, we came across a reaction with an alkene, such as cyclohexene and bromine. And in that reaction, the loosely held pi electrons were the nucleophile, and bromine was an electrophile. Now, Br2 is not normally polarized, but when something electron-rich, such as a nucleophile, such as the alkene, approaches bromine, then the electrons can shift, and we call this the ability to polarize. And so when the electrons shift, they'll shift away from the incoming nucleophile. So then this bromine will become electron-rich, and this bromine will become electron-poor. So this is called a temporary dipole. And again, it's induced by the nucleophile approaching the bromine. And this works really well for bromine because it's a large atom, so its valence electrons are more loosely held because they're further away from the nucleus, and so they're more polarizable. It's more easily able to distort its electron cloud. So as you know, when these react, the nucleophilic pi electrons will attack bromine. One of the lone pairs will come back and form a bond with the other carbon, and then one of the bromides leaves. So this is the way these two react. And in Chapter 8, we saw that after the bromonium ion gets opened up by bromide, we end up with an anti-addition of the two bromines. So this is considered an addition reaction because we're adding bromine across the pi bond. We're going to be doing a substitution reaction with benzene and bromine, so the reaction is not going to be quite the same thing. In order to get benzene or other aromatic compounds to react, we need to make bromine more electrophilic. It's simply not a very strong electrophile, and so if we add iron, it will actually create a stronger electrophile, which will be able to react with the pi electrons on benzene or in other aromatic compounds, which are less nucleophilic than an alkene. Okay, so what does iron do? So iron and bromine will do a redox reaction where iron will donate electrons to bromine, and so what we'll end up with is iron 3+ and then 3 bromide. So it's a redox reaction that eventually forms this ionic compound, iron tribromide. So after bromine and iron react to form iron tribromide, we have an additional reaction where another molecule of bromine gets involved. One of the lone pairs on that bromine can attack the iron in a Lewis acid base reaction. So this is considered the Lewis acid because it's accepting a pair of electrons, and this is considered the Lewis base because it's donating a pair of electrons. Right, so usually we talk about Bronsted acids and bases, and this is an example of a Lewis acid-base reaction. The reaction forms this complex where you notice that iron has a negative charge and then this bromine has a positive charge. And it's thought that this entire thing can dissociate or leave like a leaving group. And when that happens, we get essentially Br+, which is much more electrophilic than Br2. And that's great because if we form a stronger electrophile, then it will be able to successfully react with a weaker nucleophile. And so the pi electrons in benzene are just a weaker nucleophile than alkenes. So let's look at the mechanism. So we have benzene as an example aromatic compound. And once we form Br+, which is highly reactive electrophile, then our pi electrons in benzene can attack. So one of the carbons gets a bond to bromine, and then the other carbon ends up positively charged. Now, this is a resonance stabilized compound, and we can show the resonance contributors by doing the allylic positive charge resonance pattern. So there's the second contributor, and then we can keep going one more time. To draw the last contributor. Okay, so this intermediate has a name. Sometimes it's called the rhenium ion. So it's referring to this resonance stabilized intermediate. It's also sometimes known as the sigma complex. And a similar intermediate is formed in every single electrophilic aromatic substitution. So the pattern is always the same. The aromatic compound attacks the electrophile, right? So we need a super strong electrophile because our nucleophile is pretty weak in this case. So in order to have a reasonable activation energy, we need a strong electrophile. So adding iron enabled us to generate bromine plus. So when the nucleophile attacked, we ended up forming the rhenium ion or sigma complex. And then the last step is deprotonation. So there's a proton here, and if a base comes in to take that proton, we can regenerate the aromatic ring. In this case, the base is thought to be this iron tetrabromide. So we can show one of the bromines essentially dissociating, dissociating and taking that proton, and then these electrons swinging over to reform the aromatic ring. So then the product is our aryl bromide, and we also formed some of the catalyst again. So the iron tribromide and HBr. And those are just our inorganic byproducts.